Hello guys, welcome to my YouTube channel. In this series of lectures, I want to talk about polar codes and also polarization-adjusted convolutional codes, call it PAC codes. We will discuss about different code constructions, about the encoding of PAC codes, and also different kind of decoding algorithms, like successive cancellation, list decoding algorithm, and sequential decoding algorithms like Fanon algorithm. First, let's talk about polar coding. In this diagram, we are showing polar coding scheme, which has three parameters. N, which is the code block length, K is the data length, and calligraphic A is the set that helps us to map the data vector D into the vector U. The data vector D has length K, and using a data insertion block, we can map it to U, which is a vector of length N. After that, using a polar mapper, or we call it polar transform, we map U into the channel input vector X. This transformation is one-to-one. It means that from any vector U, we can obtain X and vice versa. Channel output is Y, and using a polar decoder, we can obtain an estimate of the data vector D. The code word length N is a power of 2. Source data D, we show it by D1 to dk. In all of the simulation results in these lectures, we will assume that the data inputs are binary, so DIs are 0 or 1. The code word is try to always use the same notation X. The receive vector is Y. We will mainly assume that the channel is binary input AWGN channel in this series of lectures. So the inputs are binary vectors and channel output is a real number. And decoded data is D hat. What are design considerations? One important design consideration is frame error rate, which is the probability of D not equal to D hat. We want to try to make it as small as possible. Rate of data transmission, R, defined as K over N, and complexity of implementation matters. Mainly the decoding complexity. We want to find decoders for our polar codes or also PAC codes, that the decoding complexity is almost linear function of N. We will see that the set A that defines mapping from D to U for the small block lengths can affect a lot the frame error rate and also the complexity of decoding. And also another parameter is transmission power. We want to see that can we get the target frame error rate with smaller transmission power or not. Let's go back to the Shannon's main theorem. For a broad class of channels, there exists a channel parameter C called capacity of the channel. It's a fundamental limit that defines the ultimate rate R at which reliable communication is possible on that channel. What is reliable communication? It means that the frame error rate goes to 0. We have an asymptotic result that when the block length N goes to infinity, for any fixed rate R less than the capacity, we can have a series of codes that frame error rate goes to zero exponentially in n. It means that the block length goes asymptotically to infinity, and frame error rate has an upper bound that it is like 2 to the n times something negative in the power. And also, reliable communication is impossible at rates above the capacity. So the channel parameter C, which is the capacity, defines a region that reliable communication is possible for the rates below it, and it is impossible for the rates above the capacity. It has some caveats. Shannon capacity is an asymptotic result. In practice, we cannot have a code of length n that is very, very large. And the way that this theorem is proved, it accepts encoders and decoders whose complexity is exponential in n times r, which is equal to the k. It's non-constructive. The way that this theorem is proved is using random coding analysis. So we know that this decoding complexity and also encoding complexity, which are exponential in the code block lengths, we cannot use it in practice. So we need to have a code with a good code construction with practical encoding and decoding complexities and good frame error rate. Polar codes are the first class of capacity achieving codes for the symmetric channels. In here, I'm saying binary input symmetric channels, but it is proof for also for non-binary symmetric channels. We only limit our study to binary input symmetric channels. These codes are based on a fast transform in the binary field F2, as we are discussing binary fields, binary input codes. And as we saw in the block diagram of the polar codes, the data vector D is embedded in a transform input, which we define by vector U. And we try to keep the same notation in all lectures. Certain coordinates of the transform inputs are fixed to 0. This one is defined by the set A, set calligraphic A, and the code word which we use, vector X, is obtained as the output of a polar transform or polar map. A polar transform or polar mapper of order n is the logarithm base 2 of the data length capital N. Is defined as the nth canonical power of a kernel matrix F. We try to use the boldface capital letters for the matrices. We define the n plus 1's canonical power of this kernel matrix F as the nth canonical power of matrix F canonical multiplication by the F. So it is a recursive construction. Yeah. So F power n plus 1 is equal to the F power n times the kernel matrix 1, 1, 1, 0. We will see for the small n equal to the 3 in our examples. How does it work? Each month, this multiplication, the canonical multiplication, embeds this matrix that are in the left-hand side in the positions that are 1. Those who are familiar with fast Fourier transform, we know that this kind of multiplying the vector u by this matrix has a computational complexity equal to the n log of n. In most of this paper, the base of the logarithm is 2. Otherwise, I will say it. Again, we review. The received data is D, and we prepare transform input U by using a set A. So U, or the bit positions that are defined by A, is equal to the D, and in the A complement, in the remaining positions, we fix it to 0. We can fix it to another predefined random values, 0 or 1, and we inform the decoder by it. But in this series of lectures, we only assume that the frozen bits, we call this frozen bits a complement, equal to the 0. And they compute the code word as x equal to the u times f Kronecker power n. This is a small example to example. Consider that the code length is 8 and the data length is 4, and the set A is equal to the 4, 6, 7, 8. And with the data insertion block, we insert the vector D with the capital small letters to show the vectors. And we assume that the vectors are row vectors. We embed it to the positions 4, 6, 7, and 8. The other bit positions are 0. We multiply it by f Kronecker power 3. This is an 8 by 8 matrix. This 4 by 4 is f to the 2, f to the 2, and f to the 2, and this block is 0. And again, take a look at to the f power of 2, which is f, and this is another f, and this is another f, and this is 0. So the construction is recursive, and we multiply it, and we get another row vector, which is the transform of this column vector, just to be able to show in one slide. And we obtain the channel input x, the code word x. Let's have a closer look of this vector. We can see many interesting things. The 8th bit is repeated in all of the bits of code word. We can see in it. So if we receive a noisy version of it, we can somehow determine it. Also U7 is in here, here, and the first one. But the worst one is U1. We only can see it in here, and it is scrambled by 7 other bits. So if we receive a noisy version of this bit, if we receive a noisy version of x1, it is very difficult for us to understand what was u1. So because of that, we don't send the data bit in u0. We freeze it to 0. But u4, u6, u7, and u8, we use them. And also this 8 by 8 matrix is the matrix that we obtain the Ritmoller codes. In the Ritmoller code, if the code block length is 8 and the data is 4, we only choose the rows that has the highest weight. This rows has weight 8, so it's good to use. This one has weight 4. Another one is this one, and another one is this one. So we use these 4 bits, which is exactly these ones. So we can see that polar codes are somehow very similar to the root model codes. Root model codes only obtains the rows that has the highest weights. It means that in this vector, we want more and more repetitions, as I described. But polar codes are a little bit different. It depends on the channel. It uses channel polarization. And if we say that each of these input bits, U1 up to U8, sees a different kind of channels, which one is more reliable? And we like to find those ones. And 4 of them that are more reliable, we will choose them. So the code construction of the model codes and polar codes are different. So the only difference we can add is the data insertion block. The difference between the root model codes and polar codes. The polar transform is the same, but this one, the way that it chooses, it's different. As we saw, encoding complexity is n log of n. The base is 2, the base of the logarithm. And it can be implemented same as the fast Fourier transforms. The decoding complexity, we will also see that it's order of n log of n. The construction complexity is roughly of the order of n. And we won't go much deep into the code construction of the polar codes in this series. Also, for the polar codes, the frame error rate is in the order of e to the minus square root of n. We saw that in the Shannon's theorem, the frame error rate goes to the 0 exponentially with n. But polar codes are only going to 0 in the order of square root of n. So this is something that we may like to improve it. We need some preliminary concepts to review also the decoding of the polar codes. We learned the encoding of it. A discrete memoryless channel W with discrete input that comes from alphabet calligraphic X and a discrete output alphabet Y, and a set of conditional probabilities W, Y given the input X, for the output given the input. The conditional probability corresponding for output sequence, which we showed by vector Y, can be written by W and Y given X, which is equal to the W Y1 given X1 times W of Y2 given X2 until probability of Yn given Xn for the input sequence of length n represented by this vector X. This definition is because the channel is memoryless. We assume that the channel is memoryless. For this discrete memoryless channel, the mutual information between the input and output, we define it by summation over channel output, summation over inputs, the probability of the input, probability of output given output given input X, and the logarithm base 2 of, we assume that the input is binary, so X is 0 and 1, the calligraphic X, probability of output given X over the probability of output. With the base row and total probability theorem, we can write like this. And the capacity of the channel is defined as the maximum of the mutual information between input and output, the maximization over the distribution of input. Another fundamental channel parameter is the Bhattacharya parameter, and is the summation over the channel output, the square root of probability of output given input, probability of output given input 1. And this is the definition for the binary input. And the Bhattacharya parameter is an upper bound on the probability of maximum likelihood decision error when the channel output is used just once to transmit a bit, 0 or 1. So, in summary, the mutual information is like the maximum rate that we can have a reliable communication. And this parameter, Bhattacharya parameters, defines an upper bound on the reliability. So we want to have a rate very close to the capacity, and the reliability ZW we want it to be as small as. Now we like to discuss the code construction and the decoding for the block lengths n equal to 2. Assume that we use two independent copies of binary input discrete memorized channel W. One of the channels we send U1 and obtain Y1. The other channel we send U2 and obtain channel output Y2. Call the first channel, first copy of the channel W prime, and the second one W second. So we can understand that the reliability of both these copies are equal to the reliability of any channel that we use to send a bit and obtain a channel output. Now instead, let's be more clever and sum those two bits with each other, XOR them, and obtain X1 and send it through one copy of the channels, and send X2 equal U2 through the second of the channels. Also, let's define the first synthetic or artificial channels for this block length 2. This 2 shows the block length, and this one, it shows the first artificial channel. Its input comes from a binary set, and output is Y2. And we want, based on the channel output Y1 and Y2, understand what was U1 in the scenario that we are sending X1, the summation of these two, through the first channel, and U2 through the second channel. And also the second synthetic channel has as input U2 and the output Y1, Y2, and U1. How come we have U1? We assume that this first channel did very good job and obtained the U1 for us. So we can use it for the second one, and based on that, can we estimate U2 correctly or not? In here, W2, the combined channel, has as input the vector U1, U2, and the output is Y1, Y2. And this first synthetic channel has as input U1, and the outputs are Y1, Y2. And the second synthetic channel has as input U2 that we want to estimate. And we assume that now the first channel did a good job and obtained U1. So the input of the channel, the output of the channel W2 is Y1, Y2, and also U1. We have these ones. We have U1, Y1, and Y2. So we want to estimate U2. Now we can understand that Just we send a bit U and obtain Y and call it the reliability by IW1. The first channel we have, first synthetic channel, has other job. We scramble its input with a random bit and obtain, and also we have the channel outputs, whole channel outputs. To obtain U1, it has a very difficult task to do. And we assume that it does it successfully. It's difficult task, but it does it successfully. So we use it for the second synthetic channel. We kind of understand that the reliability of this channel should be less than or equal to this reliability of this channel, and the second one has better. It has, if we only assume this scenario, it has the output of the input. So also from this one, we can obtain a little more information. U2 also appears in here. Notice that U2 has an effect on both Y1 and Y2, providing us with somewhat more information about U2. U2 is luckier than U1. Furthermore, because U1 plus U2 scrambles U1 by U2, as I said, there is somewhat lesser information about U1 than there was in the initial transmission set. As a result, the mutual information of the first synthetic channel is worse than an independent copy of the channels, and the second synthetic channel is the better one. This is the main result of the polar codes that polarizes channels. We assume that we want to transmit two copies, so we have two independent channels. We construct a channel that is better and another channel which is worse. So if we have a code rate half, it's much better to freeze U1, and the output and the decoder knows the value of U1, and we assume that it is 0, frozen to 0. So it is frozen to 0, and we want to decode U2. We can obtain from Y2 alone, and also from the first channel, first U1 plus U2, we can obtain information. So this is the main result of the channel polarization. This is a handy proof, but it's enough for our lectures. By using this fundamental coding theorem, a synthetic channel W2, I only call this 2, that is superior, more reliable to the initial channel W, is constructed now. On the other hand, simultaneously, another channel that is inferior, less reliable to the channel W is created. Again, the code block length is 2, the code word is X, and it is obtained from vector U, like this. And the mapping of the polar transform or polar mapper is by this F. So X is equal U times F, and it is the U1, U2 is the input of W2, and it's two copies of the channel W that we are having. X1 is the input of one channel, X2 is the input of another copy of the channels. W2, which is the overall channel, this one is the probability of the channel output given channel input. And we want to obtain two synthetic channels. I described it, so let's be more mathematical. This channel, combined channel W2, is equivalent. We saw that this F is the one-to-one transform. If we have U1 and U2, we can obtain X1 and X2. And if we have X1 and X2, we can have first and then U1. So it's a one-to-one transform. So this probability is equal to this probability, Y1. y2 given x1, x2, which is u1, u2 times f. So if we multiply it, we obtain this one. And I said that we are having two independent copies of the channel. One copy of the channel is y1 given x1. Another copy is y2 given x2. How do we obtain synthetic channels that it has y1, y2 as output and u1 as input? With the total probability theorem, we can write y1, y2, u2 given u1, summing over all u2. And using the Bayes rule, we can bring u2 from left side to right side times the probability of u2. We assume that the inputs of the overall channel, the combined channel, are uniform. So the probability of u2 is half. So we can write the probability of this synthetic channel as the summing over u2 of the probability of the combined channel times half. For the second channel that has as output y1, y2, all the vector channel output, and also the previously obtained u1 that is previously obtained through this, given the channel input u2. Again, using the Bayes rule, we can write like this, and we assume that probability of the bits u1 and u2 are half, so we can write like this. And now this one, the first one, is equal to this one, and probability of this combined channel we wrote as like this. So the probability of the first synthetic channel can be written as this, and this channel as this. If we have the reliability of the independent channels, we can obtain these probabilities. As a function of received value of y1, y2, we use Z21 for the first synthetic channel. The LLR of the output given input. This is the first synthetic channel when the input is 0 over probability of output given when the input is 1. Indicates the LLR for the bit U1. If we can obtain this Z21, if it is more than or equal to the 0, we can estimate U1 as 0. If it is less than 0, we can estimate it as 1. Similarly, we define the LLR for the second bit, probability of channel input when the input is 0 over probability of channel output when the input is 1. And we assume that we estimate U1 from this, we obtain it. And when we obtain Z2, if it is more than or equal to 0, we estimate it as 0. When it is less than 0, we estimate it as 1. We should know that LLRs of the ICE channel, ICE independent channel, yi given xi, we define it by Li. We can obtain it. And we saw that the first U1, the first bit U1 is equal to the x1 plus x2. We see it in here. U2 is equal to x2, so this one is x2. So U1 is equal to x1 plus x2. This is just XOR. This is a very well studied in the LDPC codes, that if we have the LLR, L1 and L2, in here we are assuming that the code length is 2. So if we know the reliability, the LLR of the first and second channel inputs, the summation of these two, the LLR of the summation, can be obtained from this or this approximation. Sine of L1, sine of L2, minimum of the absolute value of L1 and L2. And this is the check node operation in the LDPC code literature. Now, let's assume that we obtain U1. If U1 is equal to 0, if we estimate it at 0, now it means that we have a copy of U2 in here and another copy in here. So the LLR for the second bit should be the summation of these two. If it is equal to 1, so we have a negative LLR of it. So we can write the LLR of it equal to the L2 minus L1. This one just flips it. If we combine these two, it is equal to L2 plus L1 times and negative minus 1 U1 add. If it is 0, it means that L2 plus L1. If it is 1, it's L2 minus L1. Note that for a binary input additive wide Gaussian noise channel, Li is 2yi over sigma 2, which yi is the ice channel output and sigma 2 is the noise power. So in the case of binary input AWGN channel, which is the main channel that we are studying in this lecture series, Li's are like this, and sigma 2 can be obtained from the SNR. And from this, we can obtain the LLR of the second bit. And from the check node operation, we can obtain the LLR of the first channel. To generalize the successive cancellation decoding for any block length n, which is the power of 2, we need to functions over the vectors f and g. First vector a1 to am, call it L prime, and L second b1 to bm. The function f over these vectors is a bitwise function, and g is like this, where f and g, this small f and small g, are obtained from 18, which is this one. This is the g2, this is g function, which has as input L2, L1, and U. As you can see, L1, L2, and U. And this is the f function. You can use this or this. This is a general example for n equal to 4. I will not give example for larger n. Input of the overall channel 4 is U1 up to U4, and the channel input x1 up to x4 is equal to this vector. x1 up to x4 is this one, and L1 up to L4 are the LLR of the independent channels that we are having. Note that this left child, this one, U2, this U2 can be obtained from this second bit. It means that x2 plus x4. If we sum these two, we can obtain U2. And if we sum this bit with the third bit, we can obtain U1 plus U2. U3 plus U4. If we XOR it, it will be 0. So we can obtain this. It's the same as the first one that we had in here. And here. So the construction is recursive. So again, the left child is the summation of these two. If we sum them, we can have U1. Now, if we assume like only this part, U2 in here, look, we have U2, and if we estimate U1 from here, it means that we have kind of two copies. So we can have a G function in here. In here, we have a vector F function. Vector F function, A1, B1, A2, B2 is like that. So F function is a function of this small f of this and this, and a small f of the second and fourth to obtain this. Again, bit f function. Here was vector f function, here is bit f function. In here, we have a G function. In here, the right side is always, the right branch is always G function. And this is the vector G function. For the first bit, U3, U4, we use this one, and this one. In detail, I will show. This is the first F we use in here. This is a successive cancellation decoding tree. These LLRs are the LLRs that we obtain from the channel. L1, L2, L3, L4, which are for the binary input AWG and channels are 2yi over sigma 2. So we show it in our notation. For the first level by 0, the second level all are 1, the second level is 2. So now we use f function over here to obtain these LLRs like this. This is the first step. Similarly, again, we use the f function over these two to obtain this one. Then, if its LLR is more than or equal to 0, we estimate U1 as 0. If it is otherwise, we estimate it as 1. And then we see that U1 is a frozen bit or not. If it is frozen bit, we estimate it as 0. If it is not, we use this. Now we use a G function in here for the second bit. It's like n was equal to 2. So to obtain this one, we use a G function over L1, L1, L2, L2, and this estimate that we obtain. So we need this one, we need this in our memory, and also this estimate of UI that we obtain here, and use a G function to obtain this. Then in here, if it is more than or equal to 0, we estimate as 0, otherwise 1. And we also consider if it is frozen or not. For the second bit, now let's go back to our tree. For the second bit that we should obtain from here, we obtain these ones, U2. So we can obtain here U1, U2 we estimated, so we can obtain estimate of these ones. So we can use the G function in here to obtain these two LLRs. To obtain these two LLRs, we need a G function. G function needs these LLRs and also the estimates of U1 plus U2 and U2. And again, we use the F function in here. We need only the LLRs, and we find this LLR, and we look at this for frozen or not. If it is not frozen, we take a look at its sign and we obtain an estimate of U3. And then its right branch to estimate U4, We need these two LLRs that we have in our memory now. And also we need U3, estimate of the U3. To obtain the output of this G function. In summary, we can say that the left branches uses f functions. Just the last level is the bitwise f function. Otherwise, the other top branches are using a vector f function. This can be easily generalized to any end. And the right branches, we use g functions. To a deep discussion and a text for this part, you can refer to the pages 7 to 16 of my dissertation. See you in the next lectures.